Hi, students. This is part 3 of the lecture on geometrical optics, which covers chapters 25 and 26. And this will be the final part. Now, open to this thing. All right. So the main part, so what we've done so far is we've covered most of geometrical optics, right? And so what have we done in geometrical optics so far in the lectures that currently are before this one? So we discussed the two major laws of optics, the law of refraction and the law of reflection. All right. The law of refraction, as stated, if you're going from material with index of refraction, so instant light is in material with index refraction N1, and it transmits into a material with index of refraction N2, law of refraction, otherwise known as Snell's law, states that N1 sine theta incident is N2 sine theta transmitted. And on the other hand, if an object reflects off of a surface, particularly a smooth surface, we have what is called Hero's law, or the law of reflection, or Hero's law. And that simply is that the angle of incidence equals the angle of reflection. Now, all of these rays all exist in what is called the plane of incidence. The plane of incidence is the plane formed by the incident ray and the normal. And all of these angles are with respect to the normal to the surface. Again, normal is a fancy word for perpendicular to a surface. Okay. We also discussed applications of these various laws. Now, these are not laws of physics in a pure sense. They're not like Maxwell's equation. Remember, I told you that optics actually is an manifestation of electromagnetic theory. It is part of electromagnetic theory. And so electromagnetic theory is the only laws that describe electromagnetic theory are the Maxwell's equations and the electromagnetic force law. So in fact, you can use Maxwell's equations and derive an electromagnetic wave and then match them at the interface, and you will find what are called Fresnel's equations. I talked about this the other day, or in the last lecture. Fresnel's equations, which will predict, actually, you can derive these very laws, these very equations. And we will see in chapter 27 on wave optics that you can actually use a more primitive theory of wave theory of light called Huygens principle, or Huygens wavelets, or Huygens theory. Huygens was a contemporary of Newton, and you can actually derive the law of reflection, law of refraction, law of reflection from Huygens wavelets. So a law of physics is a behavior in the universe that is always true, that does not have a more common or more primary cause. That means it is the primary cause. The fact that I can explain these two equations based upon something else, something more fundamental, means that they are not actual laws of physics. But we use them as the main equations for optics. Geometrical optics, really all you need are these two equations. Now, we will have the thin lens formula as well. So we'll find out that we actually will have applications. One application of Snell's law is lenses. Lenses, there are two equations that you can derive from geometry, really based upon the Snell's law. I did not do any of that. But you'd find out that 1 over the object distance plus 1 over the image distance is 1 divided by the 1 over the focal length of the lens. And you have an expression for the magnetization, which is either negative d sub I over d sub O, or also the ratio of their heights, h sub I over h sub O. And it turns out that the exact same equations apply for the main application of reflection, which are mirrors. We talked about those as well, and again, fortunately, the same equations apply for mirrors as well. And in fact, you have one further equation. You know that the focal length is related to the radius of curvature of the mirror. Okay, 1/2 the radius of curvature. So that's only true for mirrors. All right. So that's where we stand. We have applied the law of refraction and the law of reflection. We have talked about them, discussed them, applied them to major parts of our technology, including lenses and mirrors. Now we're going to discuss a biological application, and that is the human eye. We're going to show how we can model the human eye very well with the very information that we learn in geometrical optics. All right. So with most of this lecture is going to be about the operation of the human eye. And for those of you who are future medical doctors and or your primary interest lies in biology or biosciences, I think this is going to be good for you, even though you may not necessarily be an optometrist. Any medical doctor is going to have to know about the human eye. It's part of the human body. So, okay, so let's talk about the human eye. So the human eye, all right. The human eye is probably, I would say, the most interesting of all optical instruments. All right, so I would say that, and it's remarkable in how it forms images and the richness of detail and color. It can not only detect color, it can also detect motion, and it has a really an amazing ability to change its focus as well. It can focus at many orders of magnitude. So now our eyes, on the other hand, even though they are amazing, they also, many of them, it is very common for people to wear eyeglasses. It's common to need vision correction. So I'm going to not only talk about the human eye and its function, but I'm also going to talk about how it is that we can use optics, not only that, use geometrical optics, not only to understand the human eye, but also to correct any kind of vision issues that allows people to have what we call ideal vision. You know, those of you who are those of us, including myself, are not lucky enough to be born with 20/20 vision. You know, we have to employ some sort of lens, one way or another. Okay. So I'm going to start off by looking at a picture of the human eye. So let me share my screen. Again, everything here is out of OpenStax. In fact, OpenStax dedicated chapters 25 and 26 to optics. I'm sorry, they dedicated chapter 25 to optics, and 26 was entirely dedicated to the human eye. All right, so we're going to start seeing chapter 26. So yes, geometrical optics is covered in chapters 25 and 26 in Cutnell and Johnson, but in a different way. All right, so what is primarily in Cutnell and Johnson? Now, there is a section on human eye and optical instruments in Cutnell and Johnson, but I think it's important to talk about it here. So here is the anatomy of the human eye. All right, if you can see my mouse. So light is going to come from the left, and the first part of the eye that the light interacts with is the cornea, And then the cornea, light refraction begins in the cornea. So the index of refraction of errors is right around 1.0. And so the cornea is going to have, it doesn't have as high, it's the second highest material as far as index of refraction is concerned in the eye. The highest is the lens. But it has the greatest amount of refraction because it has the greatest difference. And it's literally going from 1 to, I think we have refractive indices listed here for the eye. Yeah, so if you look at the eye, you see the cornea has an index of refraction of 1.38. The lens is higher at 1.41, but the greatest amount of light bending is from the air to the cornea because that's the greatest difference of indices of refraction. All right, and so light will bend in the cornea. It goes through the lens, and then it goes through this vitreous humor, which is this large orangish part of the eye here in the color, and it goes back and it goes to the fovea, which is really a set of photoreceptor cells, which is all, and it's all part of the retina. All right, so the retina is where, so we have rods and cones, and in the retina, and that information, that light gets transmitted or gets processed as information that goes down the optic nerve to the brain. All right, and so this is what's happening, and it turns out that the eye actually acts very much like a thin lens. You might say, well, the eye doesn't look anything like a thin lens. How would you say that? Well, the reason being is about 2/3 of all the refraction of light is at the cornea, and about the other 1/3 is at the lens. So this thin front part of the eye is where almost all of the refraction occurs. Refraction, yes, there's indices of refraction. These other materials in the eye, the vitreous humor also has an index of refraction. But the vast majority, almost all of the refraction occurs in the front part of the eye. So the front part of the eye, basically the combination of the cornea and the lens acts as a thin lens. And we can apply the physics that we understand from chapters 25 and 26. All right, so let me kind of state in words what I just, or state in writing what I just said in words. So we see that the about 2/3. So how do we say this? Light enters the eye at the cornea. Eye. Okay. Now, about 2/3 of the refraction of light occurs at the cornea. And the other 1/3 occurs in the lens. All right. So the eye, overall, the human eye, probably other animal eyes as well, behave as a thin lens. Human eye behaves as a thin lens. And can be understood, can be fully understood with geometrical optics. All right, so even though the eye is complicated, the physics that how we understand the image formation, or at least how we understand. I mean, processing information going to the brain. I don't understand that, but at least knowing how the light gets from the eye to the retina, I understand that. That's physics. What happens to light? What happens after it gets to the optic nerve? I don't pretend to understand that. But effectively, so all of the regions of the eye have indices of refraction. But like I say, almost all the refraction occurs through at the beginning of the eye. So the light or the information passes through the vitreous humor, or the aqueous humor, and vitreous humor. I spelled these words right. And then strikes the retina. In the back of the eye. The information then is passed through the optic nerve, and processed into the brain. So where I come into play is I understand how light gets from the cornea to the retina. All right. So the other stuff that's not part of my study, but highly interesting and important for us. Okay, so that is really how the eye works, and it really is based upon index of refraction, or the laws of refraction for the most part. Now, interestingly enough, the human eye works differently than how we would set up an optics experiment in a lab. In the lab, you might do this, right? In the lab, you might do the following. So you might have a lens, some sort of a stand of some sort, and here's an axis. Then you might say to yourself, well, there's a focal point on either side of the lens, and I'm going to put some sort of an object, maybe the light bulb or something. And I want to try to figure out where it goes. Well, as I move it around, as I said last time, maybe it goes like over here now. And if I move it in various places, the image of the light bulb will move around. All right, so essentially what I get is I get a various D sub O and D sub I combinations. Again, D sub O being the object distance, D sub I being the image distance, and the image can go all over the place. Well, we don't have that. We cannot afford that in the eye. We have a limited space in the eye. So in the eye, the image distance is fixed. And typically for humans, it's about 2 centimeters. And in fact, in this class, we're going to take the image distance to be a constant for the human eye, 2 centimeters. So what you have to do is you have to somehow try to accommodate the eye to be able to have different abilities, have different focusing abilities But your limitation is, your constraint is, you only have a set image distance. All right. So the human eye, we can't do an experiment like we could in optics. In optics, we're free to make the image, pretty much go anywhere we like. But in the human eye, we don't have that same freedom, right? So in the eye, the human eye, the image distance is set. So in the human eye, the image distance d sub I is the distance from we'll say the lens of the eye, lens cornea, to the retina, where the image forms. All right. Due to anatomy, d sub I is a constant. Your eye doesn't get bigger and smaller. It does not adjust. Your eye stays the same size. Right? D sub I is a constant, since your eye does not adjust in size. So in this class, in this course, we take d sub I equal 2 centimeters. All right. Yeah, different people are different sizes, of course, but for the most part, that's a good number. Most people have a d sub I of about 2 centimeters. No matter how big or small they happen to be, if you measure their lens to their retina, it's about 2 centimeters, give or take. I mean, and we're gonna make that assumption that it is that is the case here. So, how does the eye adjust then? Well, let's take a look at the picture again. So clearly, if d sub I has to be a constant, and of course we have no control over d sub O, we're going to focus on things far away or close up. The variable has to be the focal length, and the focal length is usually, at least like in our labs, the focal length is usually a constant. We usually cannot change the focal length. We pick up a lens off the shelf, and the focal length is what it is. But for the human eye, what changes, the only thing that's left that can actually even possibly be a variable is the focal length. So let me go back to the picture again, and let's talk about how does the eye actually adjust. All right. So the eye in our we only have 3 variables: d sub O, d sub I, and f. And d sub I is a constant, which means, and we can't control d sub O. We want to look at objects that are far away, d sub O is going to be large. We want to look at objects that are up close, d sub O is going to be small. So d sub O is whatever we want to look at. Well, there has to be another variable that is affected by a choice of d sub O, and that variable is f. And how does that get affected? Well, if you look at near the lens has these ciliary muscles. The ciliary muscles will, let me see if I can get a better picture here in the book. Ciliary muscles will actually either will accommodate the lens. So it'll either put the lens under maximum stress, or it'll have it'll have the lens in its most relaxed position. So you see in the very case that if we're looking at something very far away, this picture right here, the lens is what we refer to as totally relaxed. How far away something is, the farthest object that you can see with your vision, your eye, is called the far point. Now, for normal, or when I say normal, we really mean ideal vision, the far point is taken as infinity. Now you notice that in this picture, distance from the, well, I guess it's really the distance from the cornea to the retina is 2.00 centimeters. But anyway, d sub I is 2.00 centimeters. So you see that you see the the way the lens, this body right here, this white body, what the lens looks like when you're looking at distant objects. Again, parallel light is coming in, and you notice that the parallel light, it comes in and it focuses on the back of the eye, focuses on the retina as it should in a perfect eye. Somebody has 20/20 vision. That's how your eye works. If you're looking at something far away, the light rays come in, they refract from passing through the cornea and the lens, and they go to the back of the eye and get the image forms in the back of the eye. Now that's for looking at things that are far, far away. What about looking at something up close? Well, if we compare the pictures, it's kind of hard to see them both at the same time. You see that the ciliary muscles are actually stressing the lens so that it stresses the lens, and you see that it becomes fatter. It really changes the focal length of the lens. And so the eye is what is said to accommodate. And I'll write these terms on the board. When the eye is looking at the object that's closest, the closest object it could possibly see, which is called, in that distance is called your near point. That your eye is said to be fully accommodated at that point. So your eye accommodates, but it's fully accommodated when it's looking at the closest object and see without blurring. And again, in both pictures, we see that d sub I is a constant. And so you see light coming in from this near object, and it refracts, and again it goes to the retina. It images on the retina, which is what it's supposed to do. So the lens, the ciliary muscles, will stress the lens, and so it's considered fully accommodated. Now, we typically we have scientific instruments like microscopes and telescopes that are designed for the fully relaxed eye. Now, again, you really don't want to have your lens in a fully stressed or fully accommodated position all the time. It's much better if you're going to look at something to look at it such that your eye is in a totally relaxed type of a position. All right, and so again, that's why your instruments, scientific instruments like microscopes and telescopes, are designed for the totally relaxed eye. All right, now let's kind of remind ourselves what I just said. Okay, so what happens here? So the let me spell this correctly here. I'm not a biologist. Give me a moment. Yeah. All right. So the ciliary muscles about the eye, about the lens, contract or relax to change the focal length of the lens. Okay, and so the when the eye is looking at a distant object, it is said to be totally relaxed. The ciliary muscles are totally relaxed, and so this is actually a true term, totally relaxed. All right, when the eye looks at objects that are closer, or say that are relatively close, the ciliary muscles stress, and the eye is said to accommodate. All right. Now, when the eye reaches, when the eye is looking at the closest object that it can possibly see, or look, let me say it this way: when the eye is looking at an object that is as close as it can perceive without blurring, which is called the near point. Okay, the eye is said to be fully accommodated. Write this differently. Fully accommodated. Totally relaxed, accommodated, fully accommodated. And one more term is the longest distance that the eye can see an object. Is called its far point. All right, near point is the distance that that's the closest object you can perceive without blurring. Far point is the furthest distant object you can see. Your eyes are totally relaxed in looking at an object at the far point. Your eyes are fully accommodated in looking at an object at the near point, and your eyes accommodate in going from something far away to close up. All right, so your eyes do that, and that's just through the process of the ciliary muscle. So the cool thing is, I mean, like, when you're taking a lens, or let's say the lens of your eyeglasses. Well, lens of my eyeglasses have a focal length. That's it. They get manufactured, and that's the focal length, and that's what it is, right? Or the lens in a microscope, or the lens that you pull off in a lab. They all have a focal length, which is a constant of the lens. The amazing thing about the eye is the eye has a variable focal length. What's constant in the eye is the image distance. That's due to the anatomy. The eye can only be so big, and we take the image distance to be about, like I say, 2 centimeters. Now, we have this idea of what we call normal vision. I would say it's more like the better term probably would be ideal vision. And so ideal vision, somebody who said they have 20/20 vision, right? For ideal vision, the far point, we take the far point to be infinity, effectively infinity. We take the near point, typically by definition, a near point is about 25 centimeters. Now, 25 centimeters is the near point of somebody who's typically in their 40s. All right. So this is the 25 centimeters is the near point of someone in their 40s. Some elderly. Lose the ability to accommodate. Due to a stiffening of the lens. And that's typically called presbyopia. Right. I think it's right. And can have near points of meters. Young people can often accommodate better than 25 centimeters. But in this class, in general, we just take 25 centimeters as normal. All right, so again, for ideal vision, what we call the 20/20 perfect vision. The far point we take as infinity. The near point we take as 25 centimeters. And then 25 centimeters medically is about the near point of someone in their 40s. Some elderly people lose the ability to accommodate due to stiffening of lens. We call that presbyopia. And they can have near points of meters. They need reading glasses. Young people can often accommodate better than 25 centimeters. All right, so people in their teens and their 20s can often do even better. Now, your eye doctor will use really the same equations that we used in geometrical optics, but the eye doctor changes the equation a little bit. All right, so remind ourselves what are the two thin lens equations are. All right, we have the thin lens equation. I'll write them this way. 1 over F is 1 over D sub O plus 1 over D sub I. And we have the magnification, of course, is negative D sub I over D sub O, or H sub I over H sub O, okay? The eye doctor uses this equation, but remember that P, the power, is 1 over F. What eye doctors typically like to use an equation looks like this. Instead of 1 over F, they like to talk in terms of power. So if you look at your prescription, if you wear eyeglasses or contact lenses, you'll see on your prescription that your prescription is in terms of diopters, because the eye doctor likes to use this form of the equation. And so really these two equations are how the eye doctor basically lives. So I kind of teased my eye doctor one time. I reminded him, like, I kind of remember, I said, well, you pay your mortgage and eat and have your life all based upon these two equations. So yeah, and it basically is true. I mean, there's more to his job than that, of course, but I was being a smart aleck. But anyway, yeah, these are the equations that the eye doctor lives by. All right, and so now the let's do a couple of calculations here regarding the eye. So we'll do a couple calculations regarding the ability of the eye, and then let's discuss vision correction, because we've been talking about the ideal eye so far. Let's talk about the eye that's not ideal. All right. So I'm going to look at OpenStax example 26.1. This basically is titled Size of Image on Retina. Okay, so it says, what is the size of the image on the retina of a 1.20 times 10 negative 2 centimeter diameter human hair? Held at arm's length. We're taking that to be about 60 centimeters away. Okay. And then again, this is a constant, but take the lens to retina distance to be 2.00 centimeters. All right. So again, that's going to be a constant for this class. All right. So what is the size of the image on the retina of 1.20 times 10 negative 2 centimeter diameter human hair held at arm's length, 60.0 centimeters away? Take the lens retina distance to be 2.00 centimeters. All right. So the eye is quite frankly amazing. How we've evolved, the human eye. And this answer I think is going to be very surprising to you. I mean, again, human hair is already very small, but not too small to be seen on the retina. All right. So what do we know? Well, we're going to take the height of the object. We're going to imagine the human hair. Yeah, we were given a diameter. We're going to turn that diameter to a height. Okay, we're going to imagine the human hair as having that as a height. So that's 1.20 times 10 to the negative 2 centimeters, as we said. Height of human hair. Height, or really the diameter, if you will, of human hair. All right. We want to find h sub I. That's the height on the retina. All right. D sub O, we're saying it's 60 centimeters away. D sub I, of course, is a lens of retina distance. All right, so all this information that we know. Okay, so what are we going to do? Well, we're going to use the magnification formula. And we can really use it two different ways. So we have two forms of the magnification. We know that, and we don't actually ever have to really calculate the magnification. We just have the two forms we can find. Negative d sub I over d sub O, also equaling h sub I over h sub O. So again, magnification formula is a ratio, a negative ratio of either the image distance over the object distance, or it's the ratio of the image height over the object height. And of course, there's a nomenclature to the heights as well. Height above the axis is positive, height below the axis is negative. So yeah, we discussed that in the last lecture. But I can combine these equations, I can solve for h sub I. And so I'll do that. So I have h sub I is negative h sub O, and then d sub I over d sub O. All right. And so we get h sub I negative, we have 1.20 times 10 to the negative 2 centimeters. Then we have d sub I, which is 2 centimeters. And again, with these optics calculations, you can do them all in centimeters or however you want, because you're not really multiplying numbers together to get forces and energies, right? In this stuff, you're really just looking at distances. Let's see, 60 centimeters. You don't have to worry about it when you're talking about diopters, but again, that's just going to meters. And so we find out that h sub I is going to be quite small, negative 4.0 times 10 to the negative 4 centimeters. And that's like 4 microns. That is very, very small. Yet the human eye can still perceive it. All right, and so there's a discussion that they have afterwards talking about this size. I mean, this is very small. We're talking about around 4 microns. And so that is small, of course, but it's not the smallest the human eye can see. They discuss this truly small image is not the smallest discernible. The limit of visual acuity is even smaller than this. Okay. So we really get down to it, the limits of visual acuity. So let's kind of remind ourselves what we just saw here. We're looking at human hair that's on the order of about 4 microns. Now, wavelength of light is on the order of 0.3 to 0.7 microns. We're getting to a point where geometrical optics is very soon going to fail. And we'll have to actually handle light as a wave. That is what makes the limit of visual acuity, is that at some point light becomes a wave. You cannot see something that's smaller than a wavelength of light. All right, so limits of visual acuity have to deal with the wave properties of light. And that's chapter 27. That's our next chapter. All right. And so if, remind ourselves, recall that we cannot use geometrical optics if the objects or holes with which light interacts is less than a micron. That's general rule of thumb. I mean, 0.7 microns for red, but you know, a micron, if you're getting below a micron, which is one, you know, again, a micron is 1 micrometer. All right, that's a micron. So we're getting, the human hair is about we're talking about 4 microns. All right, so we're getting close to the limit of visual acuity with the human hair in this particular example. What about the power range of the eye? That's the next example. Example OpenStax 26.2. Power range of the eye. What is the range of a normal eye? This is OpenStax example 26.2. They have a lot of good examples in this textbook, by the way. It's a great textbook. Okay, what does that say? Calculate the power of the eye. When viewing objects at the greatest and smallest distances possible. Greatest and smallest distances possible. Okay. Assuming a lens ran a distance of 2.00 centimeters, right? And we're going to keep saying it. That's our constant. When I give you these kind of problems on the exam, I'll remind you of this as well, of course. Okay. Calculate the power of the eye when viewing objects at the greatest distances, at the greatest and smallest distances possible. So, smallest and greatest. Try that. All right. Smallest and greatest distances possible. Assuming a lens retina distance of 2.00 centimeters. All right. So we start off with the eye doctor's lens equation. That is that P, the power, is 1 over D sub O plus 1 over D sub I. Okay. Now, of course, when you're using power and you're talking about diopters, you have to have D sub O and D sub I in meters. Okay. Generally, we can be looser on units in optics, but when you're talking about diopters, you have to have the distances in meters. Okay, so let's talk about distant vision. All right, we take the far point. To be infinity. So that means that we take D sub O and we replace it with infinity. That means the power, we'll say far, will be 1 over infinity plus 1 over, again, 2 centimeters. What's that? 0.020 meters. And you find out that P far, and the power when the eye is totally relaxed, is 50 diopters. What about near vision? Well, we take the near point to be 25 centimeters. All right. All right. So how do we do this? Well, we use the same formula. So we'll say P near 1 over, and again, we need to put this into meters. So of course it'll be 0.25 meters. And then of course, 1 over D sub I, that's always 1 over the 2 centimeters, or 1 over 0.020 meters. We find out then that P near is 54 diopters. All right. So a typical eye will range in power from 50 to 54 diopters. Typical eye has an 8% ability to accommodate. Okay, 50 to 54. So a typical eye has about an 8% ability to accommodate. Young people can sometimes accommodate even more than 10%. Older people have a hard time accommodating. And so again, this is the ideal vision. The ideal vision can go from essentially about 50 near point, fully stressed, highest, at its maximum power, 54 diopters. You have to have a focal length adjusted so that you can bend light from a near object. Whereas a distant object, the rays of light are coming in more parallel. You actually can, at that point, you can actually bend light and look at something much further away. you can bend light in such a way that you only need to have a power of 50 diopters. Again, that's the typical human eye. Now, not everybody has a near point of 25 centimeters or a far point of infinity. All right, so people have, there's a lot of different vision corrections. People whose near points are not infinity, but a much more finite number, are said to be nearsighted. They can see things close up, but they can't see things far away. They need a vision correction. My problem throughout a lot of my life was nearsightedness. I had LASIK surgery back in 2001. I still wear glasses a little bit to take care of some astigmatism I still have. I mean, but the eye doctor told me, he sat down with me. I had one of the best eye doctors in the country. His name is Dr. Jack Weiss over at San Diego. So he's one of these guys that, you kind of envy, I guess. I mean, he was top of his class in undergrad and top of his class in med school. So, he's one of these guys, he's the kind of guy you want working on your eyes. He sat down with me and says, well, I look at doing LASIK surgery like shooting baskets. A lot of the shots are layups, relatively short shots. He goes, your eyes, yeah, they're like a half court shot. So I'm pretty good at what I do. I think I can get it, but you might have to have a second touch up. So, I'm very happy with how my eyes came out. I really could drive without my glasses, which, anybody who knew me at a younger age would be blown away because I had a pretty large prescription. But now, I still have the strange, weird shaped eyes, which, and I'll talk more about that actually caused me to have the problem in the first place. So I still have the extra stresses on the retina that I have to look out for. But anyway, there's people, again, people are nearsighted or farsighted. Farsighted people, on the other hand, do not have the 25 centimeter near point. Their near point is larger. And so we have vision correction. Vision correction wants to generally take for the myopic person or person who has nearsightedness, make what's at infinity appear at this person's actual near point. And for farsighted people, they want to actually take what's at the actual near point for most people and make that at the near point for the farsighted person. I mean, that's how vision correction works. That's what we're going to talk about next. All right, so vision correction for imperfect eyes. Need a new pen here. All right, vision correction. We'll start with some terms. So those of you who wear glasses, you probably already know these terms, but anyway, there's certain vision defects, right? And so we have one that's called nearsightedness. Or officially myopia. So nearsightedness is the inability to see distant objects clearly, but close objects are clear. Right? So the inability to see distant objects clearly. But close objects are clear. Okay. Then we have So essentially, what happens is the eye over converges the lights. So for nearsightedness, the eye over converges the nearly parallel rays from a distant object. And the image, the rays actually cross in front of the retina. They don't actually make it to the retina, they cross in front of the retina. Okay. The more divergent rays from a close object are conversion retina, or can, say are conversion retina. We can converge rays from a close object, but not from far away. Call that nearsightedness. And I'll show you some pictures of it. Basically, the eye is too powerful. All right, and so the eye is too powerful, so that the far point is not infinity. So essentially, let's just say the eye is too powerful, too high a power. The far point is not infinity, but a finite number. Sometimes very finite, like in my case. My eyes were, before I had LASIK surgery, I think my right eye was 20/1100 and my left eye was 2900. So I was severely myopic. So yeah, so my, who knows what my far point was. I actually probably don't want to know. All right, that's nearsightedness or myopia. Then you have what's called farsightedness. So farsightedness, otherwise called hyperopia, myopia and hyperopia. Now, these might be bonus questions on an exam someday. So let's keep this in mind. All right, farsightedness is also called hyperopia. I mean, that is the inability to see close objects. While far away objects are clear. Or while far away objects can be seen clearly. All right. Essentially, a um, a far-sighted eye is too weak. Again, a nearsighted eye is too powerful. A far-sighted eye is too weak. And it does not and it does not sufficiently converge the divergent rays from close objects. The rays of light cross behind the retina. All right, so again, I'll show you some pictures of this. The near point, well again, the less diverging rays from a long, so less diverging rays from distant objects converge on the retina. And for a far-sighted person, the near point is greater than 25 centimeters. For a far-sighted person. All right, so that's nearsightedness or myopia, farsightedness or hyperopia. Now, how do we correct these? Well, first of all, let's take a look at what this looks like in a diagram. So why would somebody be nearsighted or farsighted? So that's the next question. So give me a moment to get the right pictures up. All right. Alrighty, so let me share my screen. I have a set of pictures I'm going to bring up. Okay, so the top pair of pictures shows an example of a myopic eye. Either the lens is too strong, and you see in the upper left picture, lens is too strong, so the light rays are bent too much, and so they're bent and they form, they cross at the before the retina. Or you can have another problem where the lens to retina distance is too long, so the eye is too long. That's my problem. My eyes are shaped more like footballs, and so my issue is my lens is too long, and so my eye is too long. So again, the upper left corner, the lens is too strong. It refracts light too strongly, so that the rays cross in front of the retina. For the upper right corner, my situation, before I had LASIK, and my situation still for the rest of my life, I guess, is that my eyes are too long. And so the problem that I had is my lens was fine. It's just that the retina was still behind where the rays were crossing. The rays would cross normally where my retina should have been, or my retina was further set back. So I had LASIK surgery to essentially shave off a lot of the retina to shave off a lot of the cornea to reshape the eye such that the refraction is correct. That I made made the lens less powerful in order to be able to have the rays converge on the retina without having to wear a strong prescription. Okay. Then you have the issue of farsightedness. These are the bottom two pictures. So again, you can imagine either the lens is too weak and does not converge light well enough to actually, and the light rays converge behind the retina, or the eye is too short. So the retina happens too fast, and so maybe your lens is normal, but the eye is too short, and so and so the rays would then converge behind the lens. So again, for people who have the misshapen eyes, I mean, again, if your lens is normal and your eyes are perfect spheres, you should have 20/20 vision. However, like in my case, doctor reminded me, you may see great now. You don't have this high prescription any longer. However, do not forget that your eyes are still long, that there is still additional stresses on your retina, and if you get hit really hard, get a major car accident, or you have to be looking for anything that may detach your retina. Now, for those of you who do get a detached retina, the advice is look for maybe like a curtain going across your eyes, or sparkling lights would be the things to look for. And if that's the case, see your doctor immediately. See your eye doctor immediately. A simple surgery to weld the detached retina will save your vision. If you do not act quickly, you may have blindness. All right. And so, of course, what did I do in high school? I played football. So I did not know this information. I would not have played football if I had known it. So anyway, one good hit. Who knows? I mean, I was fortunate. Nothing ever happened to my eyes. My eyes never had a retinal tear. But again, it was probably not the smartest thing for me to do. So anyhow, that is why you have these vision defects mostly. These are called spherical vision defects. We'll talk about some other vision defects in a moment. But we have myopia and hyperopia. How do you correct them? All right. And so OpenStax example 26.3 talks about correcting nearsightedness. So let's go make some glasses. Okay. So OpenStax example 26.3. Correcting nearsightedness. That's near and dear to my heart. Okay, so the question is, what power of a spectacle lens is needed to correct the vision of a nearsighted person whose far point is 30.0 centimeters. So not infinity, but only 30 centimeters. Okay. Assume the spectacle, assume the spectacle or corrective lens is held 1.50 centimeters away from the eye by eyeglass frame. Okay. What does all this mean? So we're going to correct nearsightedness. We're going to make a prescription for glasses. What power of a spectacle lens is needed to correct the vision of a nearsighted person whose far point is 30.0 centimeters? So the doctor's, you go to the doctor's office, he's going to do he or she's going to do a set of tests and figure out what your far point is. Assume the spectacle corrective lens is held about 1.50 centimeters away from the eye by eyeglasses. So if you kind of look at me in my glasses, imagine there being a 1.5 centimeter distance from my eye to the spectacle lens. Okay, that's what we're talking about. Okay, so how do you do this? So remember this information here. 30 centimeter far point is what we have to go by. Okay, so what do we do? Well, what we want to do, all right, so the name of the game here is you want the nearsighted person. This is what your eye doctor is trying to do. You want the nearsighted person to be able to see very distant objects clearly. Okay, sounds obvious. All right. And so this means the spectacle lens, this means that the spectacle lens must produce an image. Um, 30.0 centimeters from the eye for an object very far away. All right, so you're trying to take something that's supposed to be very far away, like infinity. You're going to try to put that at 30 centimeters, which is the far point of your patient. And that's the name of the game. You're trying to put that image at 30 centimeters because that's your patient's far point. And you're trying to move what should be the far point, what should be that distant object, that image. You're trying to move it to where that particular far point is of your patient. And that's what your corrective lens should do. So, okay, so that's the name of the game. That's your doctor's trying to do. So how mathematically, how do you accomplish this? All right. So an image that is 30 centimeters from the eye. Let's kind of remind ourselves we have eyeglass frames, right? So an image that's 30 centimeters from the eye will be 28.5 centimeters. So it'll be 30.0 minus the 1.5. Remember, we have the eyeglass frames, right? So we get 30 centimeters minus the 1.5 centimeters, because you have to worry about the eyeglass frames being that much closer to the object than your eye is. So it's going to be 28.5 centimeters. Okay, from the spectacle lens. We really care about what's going on at the spectacle lens when we make glasses. All right, and so we need to know, we need to understand where is the spectacle lens being positioned with respect to the eye, and also with respect to the object. All right, and so therefore we must get d sub I. So let's kind of draw a little picture. We have the eye. There's your eye. And you have your spectacle lens. Turns out it's actually going to be, for nearsightedness, it's going to be a divergent lens. All right. So what is it that you want to do? Well, you really want to make, so you have, this is not drawing this, let me try to do a better job of drawing this. So you have the eyeball. And you have the spectacle lens. Okay. And well, we really want to see something that's off at infinity. But what we're actually going to do then is we really want to make the image, the far away image, be at, see, this is about, this distance here is 1.5 centimeters. We really want, the far point for this person is, let's say, here. And that distance is actually going to be 28.5 centimeters from the actual lens. All right. So that needs to be the far point. So what's going to happen here is that the person is going to see an image. And the image, so the object distance, the object distance is very far away. All right. So we have an object distance that's way, way, way far away. All right. So your d sub O is going to be like approaching infinity. All right. We're trying to find a distant object. Now, what's going to happen here is that the image is going to form on this other side. You have parallel lights that's going to come in. Let's say a parallel light is going to come in from this distant object. What's it going to do? Well, in reality, it's going to diverge, right? Let's say parallel light on the drawing skills are. It's also going to diverge. The reality is, if I could draw this picture right, I really want to have it diverge such that I form my bad drawing. I form a virtual image on the other side of the eye. This distance is going to be my d sub I. Okay, I want a d sub I of negative 28.5 centimeters for this eyeglass. Why is it negative? Because it's on the same side as the object. All right. So this is the object side. This is the virtual side. This is the real side. Remember that? This is the virtual side. Any distance. This is the same side as the object. Light rays are supposed to go on the other side of the lens. That's the real side. So when you have somebody that's nearsighted, parallel rays coming from infinity are going to diverge through this divergent lens, again, remember this lens, this is a diverging, concave, diverging lens. Parallel rays of light will diverge away, and the image, if you extract those rays back, they will form an image, and you want that image to occur at that far point. You want stuff, objects that are really at infinity to really be brought, have an image of that brought to the far point for your patient's far point, which is not the far point of most people, but your patient's far point happens to be 28.5 centimeters in front of his eyeglasses or her eyeglasses. And that's the name of the game here. All right, and so let's write that mathematically now. So what is the formula for the eye doctor? Well, D is 1 over D sub O plus 1 over D sub I. All right, well, again, what's D sub O? Well, D sub O is basically infinity, right? And so again, I'm trying to bring in objects that are far, far away. And so what I just showed you here is that I have 1 over infinity plus 1 over, what was that again? Well, again, that is negative 28.5 centimeters, but I have to have this in meters in order to do diopters, right? So it's negative 0.285 meters. When I work this out, I find out that the prescription for this person's glasses needs to be negative 3.51 diopters. Anybody who has nearsightedness, if you look at the spherical correction on your glasses, you'll see it is a negative value. So this person has pretty bad myopia, had about a negative 3.51 diopters. My myopia took me to about negative 9 and negative 11, if you can believe that. So anyway, that's really bad. Bumping into walls, bad. But anyway, but this is you see a negative value on the person's correction. It's called a spherical correction on your eyeglasses or your contact lenses. That tells you that person is myopic. That person is nearsighted. Okay, and so again, the image. And what does that mean? When you have a focal length that's negative, that means you have a concave diverging lens. A negative focal length, a lens that has negative focal length, is a diverging lens or a concave lens. So if you look at someone's eyeglasses, for somebody who is nearsighted, their eyeglasses are going to be thicker on the sides and thinner in the middle. They're going to have a concave lens. Okay. What about a farsighted person? Okay, that's correcting nearsightedness. Let's correct farsightedness. Okay, so correcting farsightedness is a different problem. And this will be OpenStax example 26.4. All right, OpenStax. Example 26.4. That example is about correcting farsightedness. Okay, how does the example read? What power of spectacle is needed to allow a farsighted person is needed to allow a farsighted person, yes, whose near point is 1.00 meter, to see an object clearly That is 25.0 centimeters away. And that's the near point that we're shooting for. Okay. Assume the spectacle or corrective lens. Again, same thing as we said before. Assume that the spectacle or corrective lens is held 1.50 centimeters away. From the eye by eyeglass. All right, so let's look at the same thing we talked about last time. Okay, so read that again. We have what power is needed to allow a far-sighted person whose near point is 1 meter, 1.0 meters, to see an object clearly that is 25 centimeters away. Okay, so your problem now is they can't see close objects. You can see far away, but you can't see. So closest object you can see is a meter. So you need to try to get that correct. Assume that the spectacle or corrective lens is held 1.50 centimeters away from the eye by eyeglass frames. All right, so how do we do this problem? All right, so again, what's the eye doctor want to try to do? Well, when you hold an object, so when an object is held, at 25 centimeters from the person's eyes, the spectacle lens must produce an image 1 meter away. That's what, and again, this is the patient's near point. Okay, so you have to try to get to the patient's near point. The patient doesn't have a 1 meter near point. I'll show you. The patient doesn't have a 25 centimeter point. Their patient near point is 1 meter. All right. So essentially, what has to happen here is an image 1 meter from the eye. So an image 1 meter from the eye is let's see, it is 100 centimeters minus 1.50 centimeters, or 98.5 centimeters from the eyeglass, from the spectacle lens, right? Remember, the eyeglasses are 1.5 centimeters away from your eye, so you got to subtract off the distance from the eyeglasses. So 98.5 centimeters from the spectacle lens. All right, so you have to adjust for that. All right, so there you go. So again, so therefore, d sub I will equal negative 98.5 centimeters. Since it is on the object side of the lens. Again, the wrong side of the lens, the virtual side. Okay, so how does this work? All right, and so again, so what that means then, let's see, and then the so the object's gonna be 98.5 centimeters from the on the object side of the lens. There's a little bit more for me to write. Okay, and the object. So again, that's where the image is. The image is 90. The object. So the image must be at 98.5 centimeters from the spectacle lens, as I said. Okay, that means, as I just said, is that d sub I is on the on the object side of the lens. So d sub I will be negative 98.5 centimeters. All right, where's the object distance going to be? The object distance is, well, what's it going to be? Well, it's going to be d sub O equals 25 centimeters, again, subtracting off the eyeglass frames, 1.50 centimeters. That means that d sub O must be 23.5 centimeters. Okay, again, d sub O's are always positive, right? D sub I could be positive or negative. All right, so what do you do with the eyeglass formula? Well, P is going to be, again, the eye doctor's formula, 1 over d sub O plus 1 over d sub I. Okay, P, d sub O in this case is talking about, again, we have to put these in terms of meters. So 1 over 0.235 meters plus 1 over, be careful, it's negative, right? The negative image, because it's on the object side of the lens. That's where I'm trying to form my image. Negative 0.985 meters. If I work this out, I find out that the power is going to be a positive 3.24 diopters. So again, for those people who have a positive spherical correction on their eyeglasses or contact lenses, that means that they are farsighted. That means that their correction is to correct for farsighted. So again, those are called spherical corrections. Now, there are other vision defects that get corrected. All right, and so again, I talked about farsightedness and nearsightedness, but there are other effects that get corrected, and that can be corrected via eyeglasses in many ways, or contact lenses, or we'll talk in a moment about LASIK surgery. Okay, so this is just some examples of correcting farsightedness and nearsightedness. So again, you'll have so essentially you need a convex converging lens, to correct farsightedness. Why? Because you saw that the power is positive, so that means the focal length is positive. Okay, and you need a concave diverging lens. 2 correct near seconds. Okay, those are your spherical corrections. There you are. Now, there are other types of vision problems, vision defects or eye defects, right? And so these are the spherical ones. Now, you could have one where, for instance, we could talk about astigmatism. People have astigmatism. I have astigmatism. Astigmatism is an unevenness or asymmetry in the focus of the eye. Okay. So essentially, you have two different. You don't have a spherical eye. You have many cases your eye. A spherical eye, a perfectly spherical eye, is described by one radius, right? There's one radius for a sphere. So a spherical eye or ideal eye has one radius. That describes you can have astigmatism can be caused by an aspherical eye or by an eye whose shape is described by, I guess I would say by 2 radii. One vertical, one horizontal, typically. Okay. You can also have irregularities in the shape of the cornea and possibly unevenness in the retina. Astigmatism can be caused by irregularities in the cornea or unevenness in the retina. 2 ends there, I'm not sure. Yeah. Right, so there's different, a little bit more complicated, but it actually is correctable too. Okay. So the all right. So that's astigmatism. How do you correct it? So astigmatism can be at least partially corrected with a spectacle lens having the opposite irregularity of the eye. One way of doing it. You know, when I got my LASIK surgery, they did a topographical map of my eye. So they not only knew how to correct the spherical issues that I had, but also to correct the astigmatism. So they had the eye mapped out. I mean, this is 19 years ago, right? So this is technology can only be even better now, but this was amazing to see the kind of computer pictures they were able to take. They had a very precise understanding of the topographical map of my eye. They knew exactly what the shape of my eyes are. They knew exactly what the irregularities were. So they were able to control a laser, and I'll talk about that in a moment, to actually correct a lot of this. I mean, I still have some glasses today, but I mean, my vision is significantly better. All right, so if your eyeglass prescriptions have what's called a cylindrical correction, then you have astigmatism. I've been talking about spherical corrections. If your eyeglass prescription has a cylindrical correction, then you have astigmatism. All right, so that's another defect of the eye. Now the glasses have the disadvantage that they're always stationary. Your eye moves around. There's always going to be a little bit of an error, but contact lenses, on the other hand, allow the lens to move with your eye, right? And so there's always, you get better peripheral vision with contact lenses. So the contact lenses have advantages over glasses, over eyeglasses. Other than just cosmetic. All right, so one problem with eyeglasses one problem you have with eyeglasses is that as the eye moves, it is not at a fixed distance with respect to the spectacle lens, right? Okay. But with contact lenses, the contacts actually will move with the eye. So the contact lenses rest on the eye. And move with the eye. Giving improved peripheral vision. All right, and of course, we have laser surgery. I've been talking about quite a while. So laser surgery has greatly progressed. I mean, it was very advanced when I had it when I was back 19 years ago. I was year 2001, March 2001 is when I had LASIK surgery, and it's very much progressed since then. So laser surgery notes here. Say laser vision correction. Has greatly progressed. Over the last couple of decades. I mean, mine was 19 years ago. All right. Essentially the idea with a laser surgery is that one of the things that you can do is we recall that 2/3 of the diffraction, or sorry, different refraction, 2/3 of the refraction of light occurs at the cornea. We talked about this at the beginning of this lecture. We can make a change in the refraction, so we can make it. We can change the refraction of light by reshaping the cornea with a laser. Like in my case, I was badly nearsighted. I was severely nearsighted. So my eyes were too powerful. So my corneas were flattened. To make them less powerful. In fact, I can't even wear contact lenses. corneas are too flat. So my eyes were converging light in front of the retina. Laser surgery, shaved really the cornea, outer cornea away just right, so the rays were able to converge on the retina. So to do that for a very nearsighted person required a flattening of the cornea. All right. So a farsighted person would have an increased curvature. You could also do laser vision correction, to help other kinds of vision defects. The idea is that the laser vision correction uses a laser. So with laser vision correction, high intensity electromagnetic radiation is used. High intensity electromagnetic radiation is used to ablate official word, which means to remove material from the surface. And reshape the corneal surfaces. So, and then you hear about LASIK. So today, the most commonly used laser vision correction is called laser. I don't know if I'm pronouncing this right or not, but laser in situ keratomiliosis. Sure, our doctors out there would frown on my pronunciation. And we just call that LASIK. The acronym. That is the most popular of all the laser vision procedures out there. So in LASIK, which is what I had. So in LASIK, I'll just kind of describe how it works. So in LASIK, okay, the top layer of the cornea is surgically peeled back. The doctor gets a knife and peels back the top layer of the cornea. And surgically peeled back. And the underlying tissue ablated by multiple bursts of finely controlled ultraviolet radiation. All right, so you peel back the top, they call that the flap, and underlying tissue is ablated by multiple bursts of finely controlled ultraviolet radiation. By what's called an excimer laser. All right, you peel back the flap, and you basically hit it with many bursts of excimer laser. In fact, I had a friend of mine who came to, you're not allowed to drive home after your LASIK surgery, and so when it's your time, your eye gets projected on this big screen, and so your friend gets to watch, all these bursts. It's all, he thought it was really cool, and it was almost like a war scene. All these different bursts, firings on my retina. Or sorry, my retina, but my cornea. All right, so now the lasers. So we use lasers. Why? Well, lasers are used because they not only produce well focused intense light, but they also can produce very pure wavelength electromagnetic radiation. That can be controlled more accurately than mixed wavelength light. Okay, so LASIK and LASIK, the top layer. This is LASIK now. The top layer of the cornea is surgically peeled back. Underlying tissue is then ablated by multiple bursts of finely controlled ultraviolet radiation by what's called an excimer laser. Lasers are used because they not only produce well-focused intense light, they can get as intense as you want, but they also produce pure wavelength electromagnetic radiation that is more accurately controlled than, say, mixed wavelength radiation. Okay, that's why you want to use lasers. So why is this important? Because you want to use the light that reacts best with the tissue of the eye. All right, and so the precisely 193 nanometer wavelength ultraviolet radiation, or so we use precisely 193 nanometer wavelength ultraviolet, commonly used is extremely and strongly absorbed by a corneal tissue. And that allows the precise evaporation of very thin layers. Okay, so the eye responds, the tissue, the corneal tissue responds best with 193 nanometer wavelength ultraviolet. So that's the laser, it's the excimer laser. A computer controlled program the computer program applies more bursts so we'll say applies bursts of UV radiation usually at a rate of about 10 per second. And to air, and usually they remove about a spot, usually removing a spot of 1 millimeter diameter and about 0.3 micrometers in thickness. Highly controlled. It is absolutely amazing what LASIK surgery can do. Absolutely amazing. You can see almost immediately right after the surgery. My vision was vastly improved the moment the surgery happened. I was able to read a sign across the room, and that's a huge accomplishment for someone whose eyes are as bad as mine. All right. So again, that's how LASIK works. So basically, nearsightedness farsightedness And astigmatism. Can be corrected with an accuracy. So can be corrected with an accuracy that produces normal distant vision. Say that produces normal vision. Normal or ideal vision, we'll say normal. And about 90% of the patients. And the results are mostly immediate. I mean, you get the wow effect right off the bat. I mean, I was able to see tremendously better before I even left the actual place where they did my vision correction. The procedure is mainly painless. And about 1 million Americans per year get LASIK. So it's widely successful, and many people have had great results with it. All right. So again, that's just another form of vision correction, and that's a very successful form that's permanent, and then that gets you off of having to wear glasses. All right. Let's do some problems now. All right. Let's look at OpenStax 26.1. LASIK is near and dear to my heart, so I like to talk about it a little bit. OpenStax 26.1. That says, what is the power of the eye when viewing an object .0 centimeters away? All right. So what is the power of the eye when viewing an object 50.0 centimeters away? What does that mean? Well, that means that d sub O is 50 centimeters. Of course, when I'm talking about power, I have to put that in terms of meters. So that'll be 0.500 meters. All right. D sub I, well, that's always the lens of retina distance, right? That's 2 centimeters. Or 0.020 meters. Again, that's the lens to retina distance. All right. What's the power? Well, we can just plug it into the formula right away. So P, eye doctor's formula. 1 over d sub O plus 1 over d sub I. Or 1 over 0.500 meters plus 1 over 0.020 meters. Power we'll find is 52.0 diopters. Again, if you remember, D is diopters. And that's what it stands for, capital D. So if you see that, again, you get that by having all these distances in terms of meters. Okay, otherwise you don't get a diopter. All right, OpenStax 26.3. All right, A. The print in many books. Averages 3.50 millimeters in height. In height. How high is the image of the print on the retina? So we did an example very similar. Example here. Oh, sorry. When the book is held, sorry. When the book is held at 30.0 centimeters from the eye. All right. And wherever B is going to be compare the size of the well, B is going to be it doesn't make sense. So we'll just I'll just answer it as I go along. I forget what the wording is. So A, so the print in many books averages 3.50 millimeters in height. How high is the image of the print on the retina when the book is held 30.0 centimeters from the eye? So again, we've seen a problem just like this. We did an example about the human hair. Now we're going to talk about books or a print on a book. So H sub O, the height of the object, which would be the height of the print, is 3.50 millimeters. All right. H sub I is what I'm looking for. I don't know what that is. D sub I is always 2.00 centimeters, right? That's a lens to retina distance. And D sub O, we're told is 30 centimeters. We're holding the book 30 centimeters away. All right. What is H sub I? Well, just like I did with the human hair problem, I'll set up the magnification equation. Magnification, I can state it two different ways. I can say it's the height of the image over the height of the object, or negative D sub I over D sub O. Okay, either way. And so I don't really need to ever calculate magnification. I can solve directly for the H sub I. So I just cross multiply. H sub I is H sub O. It's negative H sub O times the quantity D sub I over D sub O. plug numbers in now. So we have that H sub I is going to be 3.50 millimeters. Got my negative sign here. All right. D sub I is the lens of the lens to retina distance inside of the eye. That's going to be 2.0 centimeters. And we're holding the book 30 centimeters away. To find out the height of the print on the retina will be, I'm just going to not worry about the negative sign. We'll say it's going to be 0.233 millimeters. All right. That's the height of book print on your retina. Now, does this make sense? Well, let's see here. Right, make myself some space here. So I said that H sub I, remind ourselves, H sub I is just 0.233 millimeters. It's actually negative. An interesting point about the eye is that images actually go to the brain upside down. The brain actually has to invert all the images that it sees. So when you see a negative height, what that really means is that the images always go to the brain upside down. All right. So it's kind of as a point of, or a comment. Images always go to, I say, to the retina, inverted. The brain sets them right side up. So your brain is always setting the images. Every single thing that comes to your eye is actually upside down. Okay, so that's why this H sub I is negative, because it's going to come to the eye negative. It's going to go to the retina upside down. Images go to the retina upside down. All right. Now, the question we want to know is, well, does this size make any sense? Well, the size of the rods and cones, the photoreceptors in your eye. So the rods and the cones, the photoreceptors of the eye. All right, are much smaller than the image height of these letters. So they can be discerned. All right. So that's, as long as the rods and cones are smaller than what you're looking at, then you should be okay. All right, let's look at OpenStax 26.6. This was part B, by the way. Just the reality is, can I actually see something this small? Of course, we were able to see the human hair, so certainly we can see print on a book page. All right, OpenStax 26.6. What is the far point of a person? Whose eyes have a relaxed power of 50.5 diopters. All right, so if you recall earlier, we said totally relaxed eye power for looking at distant objects would be about 50 diopters. So this person needs a prescription. The question is, what is this person's totally relaxed eye power? So how do you figure that out? Well, you use the eye doctor equation. You say power is 1 over d sub O plus 1 over d sub I. Well, let's see here. We know what this relaxed power is. We want to figure out what d sub O does that correspond to. What is this person's far point? If we put in this person's relaxed power, then the d sub O will be that far point. So let's solve for that. And of course, d sub I is always the lens retina distance, right? So d sub I is always 0.020 meters. That's a function. That's a constant of the eye. Lens to retina distance. All right, so I can solve this. I have 1 over d sub O is going to be P minus 1 over d sub I. All right. I'll get a common denominator. So I can write this as 1 over d sub O is P d sub O, P d sub I minus 1 over d sub I, just getting a common denominator. I'll flip both equations. So I have d sub O is d sub I divided by P d sub I minus 1. Plug in the numbers now. D sub O is 0.020 meters divided by what's this relaxed power, 50.5 diopters, times against the lens retina distance of 0.020 meters minus 1. We'll find out that the furthest object this person can see is only 2 meters. This person definitely needs glasses. That is that person's far point, and for normal vision, we can take the far point to be infinity. This person has a far point of just 2 meters. This person has a myopia problem. Okay, OpenStax 26.8. A laser vision correction reshaping the cornea of a myopic patient. Myopic means nearsighted. Reduces the power of his eye. By 9.00 diopters. with a plus or minus 5.0% uncertainty. In the final correction. Okay. What is the range of diopters? What is the range of diopters for spectacle lenses that this person might need after LASIK procedure? And then that is part A. Part B asks, was this person nearsighted or farsighted? So I can read this and already tell you what that is. So without doing any calculations, was this person nearsighted or farsighted? Well, if the LASIK procedure needed to reduce the power of his eye, that means that his eye was too powerful. That means that his eye was forming an image, the rays were crossing in front of the retina, which means that he was nearsighted. Rays cross in front of the retina because the eye is too powerful. That's nearsightedness. If the eye is too weak, rays will cross behind the retina. That person would then be farsighted. All right. So again, what we're looking for here is that the LASIK procedure, we want to reduce the power of this person's eye by 9.0 diopters, but again, there's about a plus or minus 5% uncertainty in the range of diopters. So if you do a perfect job, you've reduced by 9 diopters, but you might be plus or minus 5% of that value. All right. So again, let me I'll answer part B again when we get to it. Well, let me answer part B first. I just did, but I'll write it down. So I'm going to do quickly. I'm going to do part B, and then we'll do part A. All right. So again, part B, I can just read the problem and tell you that. So part B says, if the power of the person's eye needs to be reduced, then the person's eyes were too powerful. And over converging the rays of light. Converging in front of the retina. All right. So this person was nearsighted. first of all right, so that's part B. I get that from just reading the problem. So again, as I wrote, if the power of the person's eye needs to be reduced, which is what the problem tells you, then the person's eyes were too powerful and over converging the rays of light, converging in front of the retina. This person is nearsighted. All right, now let's work on what kind of glasses this person might need if the procedure doesn't go perfectly. Sometimes people need to get touch-ups because maybe their eyes were so bad that, I mean, if you're changing your eyes by 9 diopters, that means you have really, really bad eyes. And so again, as my doctor said, he said my eyes were like throwing a half-court shot. You'll probably get it, but again, I might have a little air. So I still wear glasses, but a small, small prescription compared to what I had before. All right. So let's look at part A. So if the LASIK procedure worked perfectly, then the person would not need any vision correction. Okay. But if there is a 5% uncertainty, all right, then on the 9.00 diopter goal, okay, then 5% of 9.00 diopters is what? So simple math says you have plus or minus 0.05, that's the decimal equivalent of percentage, times 9 diopters. And so that means that we could have a plus or minus 0.45 diopters, which is a really good prescription. So if you have any glasses, in fact, you could probably live without even having glasses if it's that small. All right, so that would be what you'd have to have. So again, you might have a little prescription, but unlikely. You probably wouldn't even notice it. Okay, let's look at OpenStax 26.9. That says in a LASIK vision correction, the power of the patient's eye is increased by 3.00 diopters. Okay. Assuming this produces normal close vision. So this person was, if you're increasing this person's prescription or you're increasing the power, that means this person's eyes were too weak, which means that this person was farsighted. This person was not converging rays fast enough and missing the retina and actually converging behind the retina. So assuming, where was I? Assuming this produces normal close vision, What was the patient's near point before the procedure? You want a near point of 25 centimeters. What was this patient's near point before the procedure? All right, in a LASIK vision correction, the power of the patient's eye is increased by 3.00 diopters over what it was before. Assuming this produces normal close vision, what was this patient's near point before the procedure? Okay, so again, what are we shooting for? Well, we're shooting for near point of 25 centimeters. So this person gets LASIK. And after LASIK, his vision should be perfect. All right, so let's, according to this problem, what was it before? All right, so after LASIK, we assume the person's eyes work ideally. I usually don't try to write normal vision. I try to say ideal vision because it's really who has perfection. All right, so the near point should be 25 centimeters. Right, so that's redefined. And again, that's a near point for 40-year-old adults, but ideally, so the near point, matter what we're talking about here. So the near point is 25 centimeters. That's our definition of a near point, the distance for the closest object you can see. All right, and so that would be our DO prime, if you will. So our object, we want to be able to look at an object. Let's say after LASIK, I'll call the variables after LASIK primed. And so decibel prime means I want to be able to take a look at a 25 centimeter object, and my ideal vision, I'm going to look at an object as close as possible. I'm going to get as close as I possibly can to 25 centimeters to be able to see that object without blurring. That's ideal near point vision. D sub I is always the same inside the eye. That's a factor of the anatomy of the eye. That's the lens retina distance. So that's a constant. Now, what does that then mean? Well, essentially, what would the ideal power be? I mean, we've calculated this already. I know that it's 54 diopters, but let's work out what the ideal power should be. So after LASIK, what's this person's power? Well, again, we use the eye doctor's equation. So P prime is 1 over D sub O prime plus 1 over D sub I. P prime, again, you have to use meters for your distances. I mean, you can be loosey-goosey about your distances usually in optics, as you're not really calculating energies or forces. But when it talks about diopters, the distances must be in meters again. So we must convert these to meters. So d sub O prime would be 1 over 0.25 meters, that's 25 centimeters per meters, plus 1 over 0.020 meters. So your perfect near vision will be 54 diopters. That's what this person will have for the power of his eye at near vision. But what did this person have before? Well, we were told that we had to actually increase the power of this person's eye, right? So before he had a power of P. And so actually we have a power of P prime. Well, before he had a power of P, and what do we have to do? We had to increase his power by 3 diopters. All right. So how do you figure that out? Well, we want to solve for what he had before, right? P is what he had before. That's the perfect power he has now minus 3 diopters. Or he now has, after LASIK, 54 diopters minus 3.0 diopters. So before surgery, he walked in with 51 diopters. So his eyes were too weak. All right. Now, the question is, what was his near point? All right. So we now know what his power was. So again, we had to increase the power that he had before by 3 diopters, right? His eyes were too weak, and to get the perfect vision. We know he walked into the office with 51 diopters. What does that correspond to as far as his near point? All right, so I'm going to erase a little bit at the top here. So now we know this, 51 diopters. What near point does that correspond to? One more calculation. So P, going back to the eye doctor equation, 1 over D sub O plus 1 over D sub I. We got to solve now for D sub O. D sub O will now be his near point, his old near point. Right? D sub O prime is his new near point. He's now all spiffy with LASIK surgery. He has a near point of 25 centimeters. His eye doesn't change size. His eye is still going to be 2.0 centimeters lens retina distance. But now he walked in with those old eyes, and his old eyes had a near point of D sub O, not D sub O prime. All right, we got to solve for D sub O. So 1 over D sub O is P minus 1 over D sub I. I will now get common denominator. I did this before. 1 over D sub O. Again, common denominator would be D sub I. So P D sub I over D sub I. Actually, 2 steps in 1. P D sub I minus 1 over D sub I, and then I'll flip both equations upside down. D sub O is D sub I over P D sub I minus 1. All right, plug in some numbers. So my old near point, we have 0.020 meters. That's the lens retina distance of the human eye. Divided by, okay, so we know he walked in the office at 51 diopters. And again, the lens retina distance, 0.020 meters. Then I have minus 1 down here. When I do all that, I find out that his old near point, this far-sighted person walking in, had a near point, you work that math out, he had a near point of 1.00 meters. That means that he could not see anything closer to him than about 3.2 feet away. His near point, he had a significant farsightedness problem, and so he had to have his cornea shaped to be more powerful. It wasn't powerful enough. And so that LASIK procedure then added 3 diopters to his power to create the perfect eyes. And now he is able to he's able to now see close vision near point of 25 centimeters as opposed to 1 meter. Okay. Let's do another problem, 26.11. OpenStax 26.11. A severely myopic patient, like I, has a far point of 5.00 centimeters. That's terrible. That means that's as far away as that person can see. By how many diopters? Should the power of his eye be reduced? His eyes are too powerful. In laser vision correction. To obtain normal distant vision for him. Okay. A severely myopic patient has a far point of just 5.00 centimeters. How many diopters should the power of his eyes be reduced in laser vision correction to obtain normal distant vision for him? Okay, so what does that mean? Well, that means the far point would give you a D sub O of 5.00 centimeters. All right, so put some numbers in here. How bad are his eyes? So D sub O right now is 5.00 centimeters. Okay, and of course, D sub I is always a constant of the human eye. D sub I is 2.00 centimeters. All right. Now, what's the initial power of this person's eye? Well, do it right now. Use the eye doctor's equation. P is 1/d sub O plus 1/d sub I. And of course, I have to convert these to meters. So I have 1/0.050 meters plus 1/0.020 meters. I found out that this person comes into the office with a 70.0 diopter power. So that is pretty bad. Now we want to, what's ideal though? Well, P ideal, what's ideal? Well, ideal means that D sub O should be infinity. An ideal eye, so ideally, I could take D sub O to infinity. I should be able to see all the way out to the vanishing point, right? So I should be able to put D sub O to infinity right here. I'll still have 1/0.020 meters. And so for normal distant vision, I would have 0 plus 50 diopters, and 1/infinity is 0, 50 diopters. That should be what the normal vision is. So essentially, we want to get to P prime is, so P prime, we'll call this P prime for ideal, 50 diopters. So how much do I need to reduce? Well, we need to reduce the power of his eyes by P prime minus P. I'm sorry, P minus P prime, which equals 70 diopters minus 50 diopters equals 20 diopters. So his eyes need to have their power reduced by 20 diopters. Okay, let's do another problem. OpenStack's 26.14. All going to become eye doctors here. A young woman with normal distant vision has a 10.0% ability to accommodate. That is, increase. The power of her eyes. Okay. What is the closest object that she can see clearly? So she must be very young, because 10% is pretty good. So what is the closest object that she can see clearly? Okay, so a young woman with normal distant vision has a 10% ability to accommodate. That is, increase the power of her eyes. What is the closest object that she can see clearly? All right, so she has normal distant vision. So let's figure out what her vision is. When she can see a distant object where her eyes are totally relaxed. Okay. So, if the woman has normal distant vision, okay, then her far point is infinity. All right. You can see the vanishing point, basically. So the power of her eyes for distant vision is, we've done this calculation before, do it again. So the power of her eyes for distant vision is, so again, for distant vision, she will, again, we use the eye doctor formula, 1 over d sub O plus 1 over d sub I, all right? Well, again, for distant vision, most distant object that somebody can see with normal vision should be infinity. And then 1 over d sub O, again, that's the lens of retina distance inside the eye, 0.020 meters. So for close-up vision, far away, distant vision, she should have perfect eyes, and she should be looking at having a power, totally relaxed power of 50.0 diopters. Now, that should be her power with her eyes totally relaxed, looking at a distant as far her far point. Okay, and something basically infinity. Now, she now has the ability to accommodate 10%. That means that when she sees an object, her eyes have the ability to accommodate these ciliary muscles in her near her lens, have the ability to change her focal point of her eye to accommodate, to give her a fully accommodated power of 10% more than what you see here. All right. So her fully accommodated power would be 1.10 times this. All right. So the woman has the ability to accommodate her eyes 10%. So by 10%. That means that her fully accommodated vision, we'll call it P prime, is going to be 1.10, what we just got done talking about. So again, her fully accommodated vision, her fully accommodated power is 1.10 times her totally relaxed power. Okay, in her eyes. So what is that going to be? Well, that we're shooting for a P prime of 1.10 times 50 diopters. That means her fully accommodated power will be 55 diopters. And that's her fully accommodated power when she's looking at the closest object that she possibly can see. So what is that near point associated with that? We go back to the eye doctor equation, right? So we say, well, 1 over, so we have that P prime will be 1 over D sub O prime plus 1 over D sub I. I'm looking to solve for, I know P prime, I'm looking to solve for D sub O prime. So again, it's the same math that we got done talking about before. I'll kind of work it out over here. So 1 over D sub O prime is P prime minus 1 over D sub I. Again, get a common denominator. 1 over D sub O prime is P prime D sub I minus 1 all over D sub I. Flip the equations. D sub O prime is D sub I divided by P prime D sub I minus 1. All right, so plug in numbers now. D sub O prime is going to be the lens retina distance, 0.020 meters, divided by 55 diopters times 0.020 meters minus 1. And we find out that D sub O prime, her near point, she's very fortunate, is 0.20 meters or 20 centimeters. So for ideal vision, the person's near point, I mean, again, when we say ideal vision, we're talking about a person who's probably around the age of 40. But this person is probably in her 20s, and she has the ability to accommodate much better. And so she can see something that's 20 centimeters away without blurring. Whereas a person, who is in their 40s can see something usually about 25 centimeters away, and elderly people can be as bad as meters. Again, they have the stiffening of the eye, oftentimes called presbyopia. Okay, I have one more topic to talk about in this lecture. I'm done with vision correction. And the topic is kind of a topic that's covered in some books and not in others, but it's called the color vision, or the theory of color. What causes us to perceive color? All right. So color vision. Now, I told you about James Clerk Maxwell, one of the greatest geniuses of the human race. He's responsible for the entirety of electromagnetic theory. He's also responsible for the kinetic theory of gases, which is the first atomic molecular theory known in humankind. He also worked on a color theory, and we also know he's also was the first person to understand Saturn's rings. But again, color theory is, he was very interested in how is it that we see or perceive colors. That was something that was a great interest in. So basically, we see color. Color gives us a richness of life. We see all the beautiful hues of colors of objects and lights that are around us. But, the question is, scientifically, what is color? I mean, so really, besides the aesthetic appeal of color, things having color, we'd like to answer the question, what does color mean in scientific terms? For one. And number two, we like to answer the question of how do we as humans perceive color? I mean, it's one of those things I've been interested in since a little kid. I found colors to be, I was very attracted to colors. I mean, for me to see the colors of lights, and like stoplights, even. I mean, I found beauty in stoplights. So I mean, I found that that just seeing all these colors, I was absolutely mesmerized by colors as a kid. I don't know if that's normal or not, but that was who I was. So anyway, let's talk about a scientific theory of color vision. We don't really actually have one fully worked out. We know what a scientific theory of color vision needs to be. We know some aspects of truth about color vision, but we don't really fully understand it at this point. So let's kind of say what we do understand. So first of all, the obvious. We have noted. So we've noted that color is associated with the wavelength of visible electromagnetic radiation. Or we've already noted that. We've noted that color is associated with the wavelength of electromagnetic radiation. Okay. First and foremost, that's the obvious. All right. So when our eyes receive pure wavelength light, we tend to only see a few of the colors. And again, I talked about there's 6 colors. So again, there are 6 major colors in the visible spectrum. Okay, from longer wavelength to shorter wavelength. They are red, orange, yellow, green, blue, and violet. So again, I showed you a diagram in the last lecture, showing you these colors on the and these are the colors that I showed you these colors as as on a scale, if you will, or a plot, versus wavelength. We also know these are the order of colors in rainbows. Okay, so we know that as well. Now, when our eyes humans, receive pure wavelength light, and I've said this before as well. We tend to only see a few colors, so we tend to only see a few colors. Okay. Now, there are thousands of other hues, as you can imagine. So again, we have noted that colors associated with the wavelength electromagnetic radiation. There are 6 major colors in the visible spectrum. And again, from longer wavelength to shorter wavelength, they are red, orange, yellow, green, blue, and violet. When our eyes receive pure wavelength light, we tend to only see a few colors. Okay, so we only see a few colors at any time. But there are thousands of other hues that we can perceive. Okay, so we can perceive, for example, whole rich set of colors other than the ones I just wrote down. You can see brown, teal, gold, pink, white. And on and on and on. You can be listing colors for hours. So coming up with a theory of color vision, one simple theory of of color vision is that all of these hues our eyes respond to different combinations of wavelengths. combinations of wavelengths. It's getting worse here. Okay. So that's essentially a simple theory of color vision. Is that all of these hues are our eyes respond to different combinations of wavelengths. Okay. So the going into the biology of the eye, there are two types of light sensing cells. Okay, they're called rods and cones, or say in the retina. We'll say two types of light sensing cells in the retina. That's where the light sensing cells reside. They're called rods and cones. Okay, so we have rods and cones in the eyes. Rods are more sensitive than cones. Okay, so rods are more sensitive to cones by about a factor of 1,000. They're 1,000 times more sensitive. Okay, so you have rods and cones in the eyes. Those are not only in the eyes; they're in the retina. The retina is the photoreceptor part of the eye. The rods are more sensitive than cones by about a factor of 1,000, and they're solely responsible for peripheral vision as well as vision in very dark environments. And so they are responsible for peripheral vision and as well as vision in very dark environments. All right, so rods are responsible for peripheral vision and vision in very dark environments. Rods are also important for motion detection. All right, so And how many rods are there? There's about 120 million rods in the human eye. So there are about 120 million rods. In the human retina. Yes. All right. So rods. Again, we have two light sensing photoreceptor cells in the retina, rods and cones. Rods are much more sensitive and more plentiful than cones. So they're more sensitive. They're more sensitive than cones by a factor of 1,000. They are also responsible for peripheral vision and also vision in dark environments. Rods are also important for motion detection. You know, not only does the eye see, the eye also perceives motion. So again, you are naturally wired to respond to any motion. You know, we're wired that way from as evolution. You know, for you know, if some predator is going to come after us, any kind of motion, we sense that as danger, and we automatically react to it. We automatically respond to it. So again, the rods are important to that. Now we don't have such a problem today. We live in a civilized society, but back in we're the same people we were 35,000 years ago, right? So there are also about 120 million rods in the human retina. So we have 120 million. Now rods do not yield color vision. All right, so rods do not yield color vision. All right, not responsible for color. Okay, now, so you may notice that you may lose color vision in the dark, but you'll still be able to see shades of gray. Okay, the rods are the reason why you can do that. So you can still be able to see grayscale. Now let's talk about cones. There are many more rods. They're in the retina. They're 1,000 times more sensitive than cones. They're important for peripheral vision. They're important for vision in dark environments. They're important for motion detection. Cones are more concentrated in the fovea, that central region of the retina. And I showed you in that original picture. So cones are most concentrated in the fovea. Okay, that's the central region of the retina. There are no rods here. Okay. Now, the fovea is the center of the macula. Okay, so again, looking at the eye, the fovea is the center of the macula. Okay, that's a 5 millimeter diameter region responsible for our central vision. right? So the center of the fovea is the macula. That's responsible for our central vision, all right? The cones work best in bright light, and they're responsible for high resolution vision, okay? So unlike the rods that work well in dark light, the cones work best in bright light. Best in bright light. And are responsible for high resolution vision. Okay. The cones are responsible for color. All right, and so there are about 6 million cones in the human retina. Compared to the 120 million rods, there are about 6 million cones in the human retina. Nowhere near as many as there are rods. Okay, 6 million rods. Okay. Now, essentially, there are 3 types of cones. All right, so looking at cones, we're going to understand how do we understand color. Okay, so again, we're looking at, again, cones. They're concentrated in the fovea, which is the center of the retina. And then the fovea is the center of what's called the macula. The macula is a 5 millimeter diameter region of the eye that's responsible for central vision. Cones work best in bright light. They're responsible for the high resolution vision. There are only 6 million cones compared to the 120 million rods. Okay. So you talk about color. Color is the cones. And I believe they're named this way for the shape they take if you look at them. Okay. So there are 3 types of cones. Okay. There are 3 types of cones, and each type is sensitive to a different range of wavelengths. Range of wavelengths. I'm going to show you a picture in a minute. Show you a picture to make things a little more clear what I'm talking about. Let me find the picture that I want. I'll share my screen in a moment. Give me a moment. All right, almost there. Okay, so a nice plot that helps you understand the 3 types of cones that we have. Let me share my screen. And they simply are called basically the blue cones, green cones, and yellow cones. The blue cones are most sensitive to blue light, basically blue light right around 400 or so, 450 nanometers. The green cones are more sensitive to green light, and the yellow cones are more sensitive to yellow light. All right, so again, these are the types of cones that are in our eye. Now, how do they work? You know, we have 3 different types of cones. So essentially, a simplified theory of vision is that these are the 3 primary colors corresponding to 3 types of cones. All right, so simple theory of color vision is that the 3 types of cones we saw them as blue cones, yellow cones, green cones, and yellow cones. Serve as primary colors. Okay, so they serve as the primary colors, and the thousands of hues are just combinations of these 3 types of cones, right? So the thousands of hues are just different combinations of these 3 types of cones. Makes sense? Right? So anybody's had an art class would see that, you know, that would make sense. You have primary colors and you combine them to make different hues. So now, so for instance, so again, 3 types of cones. Each cone is sensitive to a different range of wavelengths. I showed you that plot. Simple theory of color vision is that there are 3 types of cones: blue cones, green cones, and yellow cones, and serve as the primary colors. And then the thousands of hues are just different combinations of these 3 types of cones. All right. So what might you expect? Again, anybody that's had a art class dealing with primary colors would see this. So for example, you will perceive yellow when red and green are illuminated. With the correct ratio of intensities. You get white by illuminating all 3. So we can get white by illuminating all 3. All primary colors. Okay. And so essentially it appears, you know, it would seem reasonable. So it would seem that it seems that all hues can be produced by a combination of the primary colors. Or by a combination of the primary colors. Okay, so that would seem like that would be a good color theory of colors, except it's not so simple. So, for instance, there is an indication. So again, we look at these primary colors, but it seems like the eye is more complicated than that. All right, so there is an indication color vision is more sophisticated. There is no unique set of 3 primary colors. That's a surprise. There is no unique set of 3 primary colors for the eye. So another set that works is yellow, green, and blue. So there's different sets of primary colors. Now, so essentially, in working on a theory of color vision, the 3 primary color aspect is our television. The old televisions work. The phosphors on a television is also worked by combining primary colors. But the 3 primary color aspect of color vision, or of a theory of color vision, is well established. I mean, that we do know that much. Any more sophisticated theory? Would enhance this, not deny it. Okay, so in developing a more sophisticated color theory of colors, definitely one of the fundamental aspects of it is the fact that we have a 3 primary color base. Okay. So so there are also there are many examples of colors of animals and things that we recognize to have a certain color. All right, and for instance, um, we could look at light sources. The helium neon laser always appears red. Why? Because it is the wavelength of the light of the laser that is why it has that red color. You always see the red color helium neon laser. The sun always has a yellowish spectrum, even though it has all the colors in the spectrum. Fluorescent lights always appear like a bluish white. Incandescent lights always appear to be reddish. So depending upon what kind of physical process is going on, electronic process or chemical process, those are also associated with colors. All right, and so basically, all of these aspects would fit into a theory of color. Now, again, a true, most sophisticated, finalized theory of color would actually would include everything we've talked about tonight. There is no complete theory of color at this point. Any theory of color that would possibly be true would, again, we'll talk about the three primary colors and all the various statements that I've made, about color theory. All right, and so again, this also one of the first people to actually work on such a theory was the great James Clerk Maxwell, among all those other major things he did. So that's this at this point. This is all I really have to say about geometrical optics. All right, so the next subject we'll then talk about would be where we cannot make the approximation that objects and holes are much bigger than the wavelength of light, and we have to use wave properties light. That will be the subject of chapter 27.